Okay, everyone. Welcome to Easy Fun Coding Seminar Series. Tonight, we are very glad to invite Professor Brian Dean to be our speaker tonight. Professor Dean is the chair of Computer Science Division at Clemson University. He received a PhD and bachelor from MIT. His research is in computer algorithms with application in biomedical data. And he directs the algorithm group in School of Computing at Clemson University. He's also a recipient of National Science Foundation Career Award. Professor Dean is well known as the director of USA Computing Olympiad. Many of us are interested in participating in USA Computing Olympiad. For those of you who don't know about the USA Computing Olympiad, it's a scientific foundation which trains students, high school students, to participate in International Olympiad, Informatics Olympiad. And Professor Dean and his team select nationwide top high school students every year to attend a summer training camp. And from there, a team of 4 students, I think, are selected to represent the United States to compete in the International Informatics Olympiad, which is the most prestigious programming contest for high school students. So we are very glad to have Professor Dean tonight. We believe he has lots of great insights to share with us, both as a computer scientist and as an educator. So we invited him to give a talk a few weeks ago, and Professor Dean is really warm-hearted. He agreed immediately, very really made himself available and is eager to help the students. So, well, thank you for being here with us tonight. And without further ado, let's please join me in welcoming Professor Brian Dean. Thank you.
All right. Thank you so much for the kind introduction. It's really my pleasure to be here tonight. It's always fun to speak to students and parents and people interested in computing. So let me see if I can switch to my slides here. Can you guys see my slide view okay here?
Yeah, we can see it.
Okay, awesome. There are quite a few things I wanted to talk about tonight. I might skip 1 or 2 things depending on time constraints. But overall, what I had hoped to talk about was a little bit about myself, kind of my own personal journey, how I got interested in computing when I was your age as a student, kind of my own journey through computer science. What do I actually do as a computer scientist, as a professor? So some of my own current research problems, trying to motivate kind of what are some interesting things that computer scientists do. Sometimes it's not so easy to know that as a high schooler. You might see depictions of computer scientists in movies that are very unrealistic from based on what computer scientists actually do. And then, of course, I will talk about my role as the director of the USA Computing Olympiad, which is an organization that is dedicated to supporting computing at the high school and at basically the K through 12 level, and that trains and selects top students nationally in computing. So lots of fun stuff to talk about. As much as possible, it would be fun to make this interactive, so I'll keep one eye on the chat window. If you guys have questions, please feel welcome to write them into the chat window. And I think there's also going to be some time at the end for questions and answers. So don't be shy if you've got questions, feel welcome to ask. So about myself, I guess my background has already been introduced. I grew up in Charlotte, North Carolina originally. Did all of my undergraduate through PhD work at MIT up in Massachusetts. And now I am a professor at Clemson University. So I'm the chair of the computer science division in Clemson's School of Computing. So I'm living closer to where I grew up. Now I live in South Carolina versus North Carolina. A little bit about how things got started for me. So I was really into computers and programming when I was your age. In middle school, mostly, I think, is when I started getting interested in writing programs. And back in the day, I would write computer games for my friends. That's kind of how I got interested in programming, by writing computer games. And my friends would pay me in M&Ms for writing them computer games. It was a wonderful business model while it lasted. It doesn't scale very well, I guess. But I really began to enjoy programming and problem solving and all things about computing and also mathematics. But then I came across an even better reason to improve my skills and become a better problem solver. And that reason, of course, was sibling rivalry. So I have a younger sister who's 2 years younger than me. And when I was an 8th grader, my then 6th grade sister jumped 2 years ahead in math and was then in my math class. And this was unacceptable. It was, everyone was kind of making fun of me that my little sister keeps, doing better than me at math. And unfortunately, that situation persisted. But I think the competition with my sibling was one of the reasons that I kind of, got better myself at mathematics and at computing. It's interesting how things move forward. So nowadays, my younger sister actually has a PhD in math from Harvard and is a professional mathematician. And so I've put a quote from her webpage on what she studies. I think I understand all the words, but not all of what they mean. So she studies some very, very deep and abstract concepts in mathematics. So just a warning to you all, if you do study mathematics, beware where it takes you down at the end of the road. You can get into some very interesting but very abstract stuff. And part of what I want to talk about is a little bit about the difference between computer science and math, and also the similarities between the two, because the two fields actually share a lot in common, and you can gain a lot by being good at mathematics and computing and vice versa. So we'll come back to math in just a second, but let's talk a little bit about computing and computer science, the field that I'm in. So what is computer science all about? It must be about computers because it has that in the title, but it's about something more than that. There's a famous quote by a computer scientist named Edgar Dijkstra that says, "Computer science is no more about computers than astronomy is about telescopes," which I think it's a wonderful quote because it really does highlight the fact that a computer is just a tool, and computer science is something much deeper than just computers. We're using technology, but we're it's almost more about problem solving and almost mathematical thinking, and using computing as a tool to solve large real world problems and have an impact. So there's a lot that you see about computing, say in movies and popular culture, that portrays computing in a certain way, and it's not always positive. There are lots and lots of myths out there about computing. This is a cartoon, if you guys know the cartoon character Dilbert. He's a wonderful caricature of everything that is kind of like the stereotype about someone who works in technology. So there's a lot of myths out there about computing. Many of them are kind of negative stereotypes, and I think a lot of these are preventing people from wanting to go into computing because they think there's all this kind of negative association with computing. They think that computer scientists don't solve real world problems, that they kind of sit in their cubicles and they write code just for the sake of writing code, but there's no impact on the real world. They think that it's a socially isolating field. They think that all computing professionals are nerdy guys with beards and ponytails. I guess that one I can't really argue with because that's me. But they think that there's nothing exciting or fun or engaging about computer science. And I think all of these are actually not true. There is a lot about computer science, a lot more richness to computer science than you might see from the way it's often portrayed. Computer science is a very collaborative field. You work with people in all sorts of different disciplines. It addresses problems that are extremely important in reality. I'll just skip through. Almost every talk like this has a slide that has statistics on why there's a lot of jobs in computer science. I'll just skip that slide and say there's a lot of jobs available in computer science. It's a field where finding interesting options for future employment. There are just so many different directions you can take computing as a career. So what are the things I love about my job, about being a computer scientist? One thing is that computing moves fast as a field. I'm really never bored, and sometimes I'm frantically scrambling to keep up with the latest advances in technology. I need to learn new computer languages every day. I need to learn new technologies. There are lots of really cool things happening in computing. We're on the verge of, self-driving cars, personalized medicine, using computing to analyze your genetic information to suggest personalized therapies that can cure diseases. All sorts of really cool stuff on the horizon, a lot of which didn't even exist 10 or 15 years ago. And so the field is evolving extremely rapidly. We have technologies like artificial intelligence that have advanced so quickly in the last few years. It's been quite remarkable. So it's a fast-moving field. And so that's a good thing, I think. If you go into computing, you're always learning and you're always evolving. You never get bored. One other thing I love about computing is you have the ability to have a huge impact on the world by investing very few resources. There's something like 1 billion cell phones out there. And so if tomorrow one of you writes a useful cell phone app, 1 billion people can be using that the next day. And that didn't take a huge outlay of resources to build that app. In many other fields, if you want to have impact, you need to spend millions of dollars and build a factory to produce things or whatnot. In computer science, you can write a useful cell phone app living in your basement in a day, and then 1 billion people can be using it the next day. So you can have a huge amount of impact with very little investment upfront. So that's an exciting thing about the field. One other thing that's really cool about computing is it's becoming a central part, not just of computing itself, but of almost every other discipline. So nowadays, innovations in like chemistry or biology or other fields are often happening because of kind of collaborations with computing. You might hear the phrase computing plus X used a lot, and that kind of reflects the fact that you can make all sorts of really interesting career choices by taking computer science and other ideas in computing and combining that with other fields. Lots and lots of ways you can do that. You can apply it to science, engineering, even arts and humanities. You can do really cool stuff. When I was an undergraduate, I was really into computer generated music. So lots of really cool things you can do by combining computing with other fields. And then finally, this kind of goes back to my roots being interested in mathematics. I get to use really cool problem-solving techniques in mathematics and things that are a lot of fun. I get to really use my brain in interesting, creative ways, but I get to do so in a way that solves problems that are extremely practical in the real world. So I assume many of you are interested in mathematics or enjoy mathematical problem-solving. So computer science is a really wonderful way that you can use mathematics and problem-solving to solve real-world problems. So it's a great line of study for those interested in mathematics. So just to reiterate, computer science and my particular field, algorithmic computer science, where you're kind of trying to solve large-scale problems quickly, it's kind of becoming the center of many sorts of combined efforts with other fields. So science, engineering, the arts, commerce, health, society, all sorts of different walks of life are being impacted by computing. And so there are just so many opportunities out there to combine computing with other applications. I'll talk about a few of those in my own research in just a few minutes. This is a fun cartoon. One of my favorite cartoons is called Xkcd. It's a cartoon that often talks about technology and things like that, which this is also kind of getting back to mathematics. But it talks about different fields of study arranged by their levels of purity. It's a wonderful little cartoon that it talks about how if you're a biologist, chemists can kind of make fun of you because they can say, well, biology is just applied chemistry. And then a physicist might make fun of you because, well, chemistry is just applied physics. And then this is making fun ultimately of the mathematician whose field is so abstract, the mathematician is way off on the side, kind of disconnected from everything else because they're even at a more abstract level than these other more applied fields. Kind of the question that I get though looking at this slide, this cartoon is, where does computing and computer science fit on this spectrum of all the different sciences. And how is it different, say, than mathematics, like what my sister studies? I think there's a lot in common between the two. So you can study mathematics and computing from both a very theoretical perspective or a very applied perspective. Both of them can be combined in interesting ways with other disciplines. And both of them have really cool ideas and problem solving. I think the main difference and what draws me to computer science more so than math, and both being wonderful fields, of course, is that computer science has a little more to do with creating things, with building things, with implementation. So you get to use your mathematical problem solving skills and build, software and solutions that can actually have real world impact. So I think that's a really cool way to use your mathematical, the mathematical side of your brain and have a huge amount of impact in practice. There's a lot of interesting applications in computing that they look really cool and fun. And sometimes you wonder, like, is this actually practical? So, you can kind of pose interesting problems. Just two quick examples are one of my colleagues at Clemson does research on aging of faces. So he can take pictures of somebody's face and predict what it will look like when that person is older. So here's a picture of the actor Sean Connery when he's young, and then when he's old, both as a predicted face when he's old and with his actual face when he's old. So the prediction was pretty accurate. And this other example is a professor at MIT who I know as a fascinating fellow. His name is Eric Demain. He actually joined MIT as a professor when he was 20 years old. I think the youngest faculty ever to join MIT. But one of his research interests is computational origami. So if you want to fold a turtle or a zebra out of a piece of paper, he has an algorithm or a program that will tell you how to do that. So these are all kind of cool applications of computing, as many other things are. But you might wonder, is there any sort of practical use for these sorts of applications? And it turns out you don't have to look that hard to figure out how you can use this sort of technology. What would be an example of an application of predicting the way your face looks when you're older, for example? Anyone have any thoughts on that? That's one way to put it. Finding murderers. If you have a missing person who disappears when they're young and you'd like to predict what you guess their face looks like in the present day, this could be technology that could be useful. How about computational origami? What sort of use could that have in the real world? Architecture and art? Sure. There's actually a whole bunch of different, yes, space shuttles and packaging. On the slide here, there's an example of, on the right-hand side, a stent, which is something you insert into somebody's, like an artery, and then it unfolds itself and props the artery open. On the left, this is an example of like a space mirror, so that you would put it in like a rocket or a space shuttle and in a folded up state, and then it unfolds once it gets into space. So there's actually a lot of cool applications of folding and unfolding that you wouldn't maybe necessarily think of right off the top of your head. This is one thing I love about computing, is that you get to solve problems that have a high coolness factor, but that also have really cool applicability to problems in the real world. So let me tell you a tiny bit about some of the things I work on as a computer scientist. This is a picture of my research lab, the students that work with me in my lab. It's actually inspired by my wife, who is also a professor at Clemson. She's a bioengineering professor. And she unfortunately makes fun of me all the time when I talk about my lab, because she has an actual lab with things like test tubes and atomic force microscopes and fancy equipment. And she jokes that I don't have a lab. She says I have an office where we all sit around a whiteboard and write equations and try and solve problems. And so to make myself feel like I have more of a lab, we took a picture of ourselves all wearing lab coats. We all made lab coats for ourselves. So we feel like real scientists now when we stand around and talk about our algorithmic techniques. And you can see us here mixing a beaker that says theory with a beaker that says practice, because our research has, it kind of combines problem solving in theory with interesting applications in practice. So let me tell you a tiny bit about some of the work that I do, specifically in the area of combining computing with medical applications in kind of in the biomedical domain. And here, along with quite a few collaborators, I work on research that studies certain diseases. We focus on mostly neurological diseases. So things like epilepsy, autism, and Alzheimer's disease. So very prevalent neurological disorders. And we're trying to see if we can somehow use computer science and algorithms to improve therapies and our understanding of these different diseases. So all of this got started actually with a collaboration with a neurologist who studies epilepsy. He actually studies brainwave data, which is really fascinating stuff. This is when you hook up, a collection of like 20 electrodes to your scalp and you measure the electrical potentials over time. Basically, kind of you measure how your brain is thinking in different places. And what you get out is a picture of all of your brain activity at different points on your scalp. And then from that, you can try and figure out, is there something wrong with the underlying brain that you're looking at? So typically, what happens if someone has epilepsy, they have seizures. And if you're having a seizure while you're hooked up to an EEG machine, it's very obvious. The signals start going haywire and you get a lot of very high amplitude signals. But most of the time, when somebody has a seizure or something, they're not immediately hooked up to an EEG machine. They go to the hospital and say, hey, I think I had an episode or a seizure. And then they hook you up to an EEG machine and measure your brain activity. And it looks a little bit more normal then. You're looking for very, very subtle cues that might indicate something is wrong. And things in your EEGs that might look like they're serious or weird are actually very normal. So this is an example of a brainwave data from a patient. And the really big spike you see in the middle is actually the most normal thing. That's actually the patient blinking their eyes, because that generates a huge electrical signal in your brain. So, really big spikes are actually very normal. This high frequency noise here, that's actually muscle activity, like you're scrunching up your forehead, for example. It turns out that the thing you're looking for if you're trying to diagnose epilepsy are these tiny little spikes down in the corner. If you have these present in your brainwave activity, that's a strong signal that you might have epilepsy. And so working with this neurologist, we designed machine learning algorithms that could look at brainwave data from a person and try and predict whether or not they have epilepsy based on looking for these sorts of patterns, which is much easier said than done, because brainwave data has all sorts of weird artifacts in it and whatnot. Eye blinks and muscle activity are all trying to kind of obscure these little tiny patterns that you're looking for. So that's kind of how things got started. We then moved to collaborate with another group that looks at brain imaging with MRI. So this is using magnetic resonance imaging. You might have seen pictures of an MRI scanner. It's this giant tube that you put the patient in, and it uses magnetism to basically figure out what parts of the brain are thinking heavily. And you can use this for all sorts of cool activities. You can move your arm while you're in an MRI scanner, and the part of your brain that has to do with moving your arm lights up. And so you can figure out what part of your brain is related to different types of activities. And so what we have done with MRI scans of brains is we turn them into networks. So we look at regions of the brain that are thinking in a very highly correlated fashion. So maybe this part of your brain and this other part of your brain have very similar sorts of activity patterns in the scanner. And so we can connect those two regions of the brain with a link and make a network out of your brain, where regions of the brain are connected if they have a very similar sort of thought pattern behind them. And so after turning your brain into a kind of a network model that kind of reflects what parts of the brain are thinking in similar ways, now we can actually study brains in a way that computer scientists are very familiar with. A network is a very familiar object to a computer scientist. And we can look at patterns in these networks and try and investigate interesting biological hypotheses by doing that. So looking at connectivity patterns in brains that are indicative of, say, having autism or Alzheimer's or whatnot. So we have a lot of current projects underway that are investigating these sorts of ideas. So these are also interesting problems because it illustrates something that computer scientists are very good at, or supposed to be good at in what they do. It's a notion called abstraction, where you can kind of study a general concept that applies in lots of different situations. And so just to give you an example, when we study brain networks, we're looking for perhaps regions of the brain that are kind of influential in terms of how well they're connected with other regions of the brain. That might tell us something about connectivity patterns related to disease, for example, looking at how those connected regions change with people that have disease and that don't have disease. But you can also end up studying the same problem in very different contexts. So for example, when Google ranks pages on the web, they're actually looking at the exact same problem because the World Wide Web is a giant network. Every web page has links to other web pages. And based on those links, Google suggests the most influential pages, the pages that should be a good answer to your search query. So if I search for the word autism in Google, it looks at the structure of the World Wide Web as a giant network and tries to suggest the most influential pages. In a social network, you might also, where you have, each node in the network is a person and you have a connection between two people who are friends, you might be looking for, again, individuals that are highly influenced, that they have high influence because they're well connected in the context of the network. It's the exact same problem. And so as a computer scientist, I can actually use methods that are developed for network analysis to solve all of these problems. So we've kind of been running the algorithm that Google uses to rank web pages. We've been running that on brains to try and figure out what regions of the brain are well connected or influential. And these same algorithms can be used to analyze social networks. So that's one really cool thing about computing is you can develop general purpose solutions that apply to a wide range of problems. You just change the meaning of the network and the solution can be applied in different areas. So I'll give you one other example of taking an algorithm that we developed for one problem and then using it in a very different way, but for essentially the same problem. And so we actually, a while back, wrote an algorithm that can automatically find bugs in computer programs. So here's a computer program that has 2 lines that have bugs in them. How might you automatically find a bug in a computer program? There's a couple things you can do, but one kind of obvious approach is you run the program on a bunch of test inputs. And sometimes the program will give you the wrong answer, and sometimes it will give you the right answer. So you test the program out on a whole bunch of inputs. And so here, I've got a whole bunch of inputs. The input here is just 3 numbers. If I give it 3 numbers, sometimes the program fails, and then sometimes the program passes the test case. And so you can look at which lines of code were actually executed when the program failed, and which lines of code were executed when the program didn't fail, when it gave the right output. And a bug or a likely bug would be a line of code that is suspiciously often executed when the program fails versus when it didn't fail. So this first highlighted line here is executed in 3 out of the 5 cases where the program failed, and it's never executed when the program passed the test case. That's a little bit suspicious. It seems to happen much more often when the program is doing the wrong thing than when it's doing the right thing. So you can look for lines of code that are kind of overly expressed in the situation where the program is doing the wrong thing. And that suggests locations where you might find bugs. So we wrote this algorithm, and it was pretty effective at finding bugs in computer programs. But then if you think about it like a computer scientist, you're like, well, where else could we apply this same idea of a program? And so we tried to apply it actually to the human genome. Because if you step back and look at things from a big picture perspective, your genome, inside all of your cells is just a giant computer program. It's your operating system. It codes for all the proteins that make your cells do what your cells do. And so if you have a mutation in your genome that causes you to get sick or have a disease, that's basically your programming, your operating system has a bug in it, right? You've got a line of code in your operating system that's wrong, that causes some sort of faulty output that causes you to get sick. And abstractly, it kind of feels like, well, sure, we have an automated debugging algorithm. Why don't we just debug humans by running this on the human genome? And that's essentially what we have been doing recently. I have a current graduate student, and we are doing what are called genome-wide association studies, where we have a whole bunch of examples of sequenced genomes of people with a particular disorder, and then a bunch of sequenced genomes of people without the disorder. And we are looking for bugs that are kind of mutations in the genome that are more highly expressed in subjects that have the disease compared to those that don't have the disease. It's actually the exact same problem if you look at it the right way, and we can apply the same techniques. So this is one thing I love about computer science, is that you can develop techniques for one problem and then adapt them to all sorts of other related problems. Unfortunately, this approach is still challenging. There are aspects of biology that are much more complicated than computer programs that make this sort of approach not work as well as it could. So we actually had to develop another layer of sophistication to make our approach actually work well. And so let me tell you one final direction of study for this debugging humans application that also kind of allows me to kind of evangelize about some recent results in computer science. So have any of you guys heard of the term deep learning? It's kind of one of the buzzwords now in computing and in AI, artificial intelligence. So in recent years, maybe 5-10 years ago, AI took a giant leap forward with this technique of deep learning that kind of makes what's called a neural network that mimics kind of the way a brain works. And AI was able to, using these deep neural networks with many, many layers of artificial neurons in them, AI could identify pictures extremely well. So this is an example of a picture that it identifies as a red fox, not a kit fox or a gray fox, but a red fox. And it's remarkable that, to a computer, this is just a bunch of numbers, the intensities of pixels. But feeding this through a neural network, it can identify with pretty good accuracy what this is a picture of. And AI didn't used to be able to do this until recently. So that's a really big deal. Although there are still some limitations. There's actually a programming contest that I run locally in my region called the Bev Ross Contest. Bev Ross is the Lithuanian word for beaver, which is the mascot of the contest, because the beaver is kind of like an animal that does engineering. And so this is a contest that originated in Europe, actually in Lithuania, and we've been importing it into the United States. I'll say a little bit more about it later on. But I actually, just for fun, ran the mascot of the Bev Ross Contest. It's this little cartoon beaver with a US flag on his belly. I ran that through a deep learning neural network classifier, and it said this is clearly a basketball, which I can kind of see where it got that idea, but it's not exactly right. And so I thought, well, maybe the US flag on his belly is causing it to think, to get a little bit confused. So I took that off and I said, okay, now what is this object? And it said, oh, clearly it's a lampshade, which is also not quite right. So I guess deep learning does a really good job at identifying images unless they are cartoon beavers. But there are actually some more serious weaknesses that showed up in these early algorithms for image analysis. So this is a really cool example of what some researchers elsewhere came up with. They came up with a sticker that you can stick into an image, and that will actually trick a neural network into classifying it wrong. So the top image is correctly classified as a banana, but if you put the sticker on the image, now it classifies the image as a toaster. So they were able to kind of reverse engineer how the neural network worked and cause it to give an incorrect classification. And this has been a serious issue with modern artificial intelligence. You could say it's an issue with robustness, or with machine learning not quite doing what you want it to do, or being easily tricked. So up top here, it is kind of funny, I agree. So here's an image of a cat that's correctly classified as a Persian cat, but there are ways that you could actually change just a few pixels in the image in an imperceptible way to a human, but now the image is classified as a toaster. And I'm really not sure what's the deal with toasters, why people want to keep misclassifying things as toasters. But this is a serious problem. This stop sign right here, researchers have figured out a way to put a few black and white stickers on the stop sign, and now a deep learning neural network incorrectly classifies it as a 45-mile-per-hour speed limit sign, which is a really, really bad thing to do if you're building a self-driving car. Instead of stopping, it would accelerate. The image on the left here of a wolf is a kind of a well-known cautionary tale in AI, where some image analysis researchers were trying to get AI to identify pictures of wolves, and it did a great job until they realized that it wasn't actually identifying the wolf at all. It was identifying the snow in the background. So if they showed a picture of anything with snow in the background, it would call it a wolf. So sometimes, garbage in, garbage out, computers are not really learning what you want them to learn. This final example I'll just kind of mention of this really strange figure was a group of machine learning people were trying to ask a computer to automatically learn the shape of an organism that would be the best at jumping high. So, subject to a constraint saying that you have at least a certain amount of mass, you want to make a shape of an organism, maybe like a human shape or an animal shape or something, but it has to be able to jump as high as possible. And what the computer came up with was this giant stick, kind of one giant leg with a box at the top, which is kind of like the head. And to jump, what this creature does is it just kicks out the stick and it falls to the ground, which is not really what you want when you're jumping. But the way the researchers coded this up, that counted as a jump because it was very far off the ground for a split second. So computers are still pretty dumb in a lot of ways. But this is kind of bad because if you're trying to build like a self-driving car, you don't want it to be dumb or you don't want it to be easily tricked. And so how can you address these sorts of issues? So another recent milestone or advancement in AI was the development of something called a GAN, short for Generative Adversarial Network. And this is a really cool idea. This is like basically using another neural network to train your neural network to get better. So you actually have two neural networks pitted against each other in almost a competition. You have the original neural network, which is trying to, say, identify pictures of cats. And then you have an adversarial network that's trying to trick the original network. And it will generate pictures of fake cats, and it gets rewarded if it can trick the original network into, saying yes to a picture of a fake cat. So you have these two networks kind of wired together. One is trying to recognize real cats, and the other one is trying to trick it by generating pictures of fake cats that look realistic. And this is kind of cool because you can wire these two networks together and basically kind of slowly back away and let them train together. So as they both train at the same time, the original network gets better and better at differentiating real cats from fake cats. It's harder to hack this sort of network. And the adversary also gets better at generating pictures of fake cats. And so it starts, so they both kind of get more and more proficient and more robust at the same time. And this has been a major way that we've been able to address some of the original weaknesses with, misclassifying a cat as a toaster. If you can kind of train your network against an adversary like this, it can really help. By the way, so one of these pictures here is a fake cat generated by a neural network. Anyone have a guess as to which one? Left or right cat? Which one is the fake cat? We actually have a difference of opinion. Several people say left, several people say right. So you can see that the neural network actually is doing a pretty good job of generating fake cats because it's not easy to tell. In fact, these are both fake cats. So I guess the lesson here that we have been importing into our own research is that if you put an adversary in the picture, sometimes that can make your AI more robust if it has to actually compete against an adversary that is willfully trying to break it. And so we actually are doing this now, just kind of a high level idea, in our genome-wide association studies. The things that we started out, in their infancy as debugging computer programs, now they're debugging humans by looking for mutations that cause disease. And to make these work really well, we've now incorporated an adversarial component where we're trying to figure out what mutations cause a disease. And we have an adversary in the picture who is trying to kind of say, well, your choice of mutations was really good, but it didn't do a good job differentiating these people that have the disease from these people that didn't have the disease. And so you can actually phrase this sort of problem using the language of game theory, which is an area that I also study, where you can come up with a really robust solution because it has to actually overcome this adversary that's trying to kind of choose weights on your inputs in a way that makes your solution look bad. So lots of really cool stuff. There's a lot of interesting connections between recent innovations in AI and all sorts of other problems that you could be looking at. So this is just kind of a glimpse at some of the problems that we're studying in my lab, and just kind of a highlight of how computing can be applied to a very wide range of interesting real world problems, in this case, kind of biomedical problems. So let me move on and talk a little bit about the third component of the talk is about my work in educational outreach with the USA Computing Olympiad and other organizations. So as was mentioned, I'm the director of the USA Computing Olympiad. I also am a regional director of this Bev Ross Contest, which I would encourage you guys to also look up if you haven't heard of it. It's a wonderful contest on computational thinking. It's kind of a slightly lower level contest than the Olympiads, but it's a wonderful on-ramp into the world of kind of algorithmic thinking. The problems in the Bev Ross Contest don't require any programming at all. So it's a wonderful way to kind of train your mind to think like a computer scientist, but without the initial step of learning to program, which is a pretty big hurdle sometimes for people just starting out. So definitely have a look at that contest. It's designed to be integrated into schools very effectively. So that's a resource I would encourage you to have a look at. Let's talk mostly though about the USA Computing Olympiad. That's where I spend most of my outreach time. So the USA Computing Olympiad trains a team of the very best students across the USA at the high school level to attend a programming contest called the International Olympiad in Informatics. It moves from country to country every year. So every year it's in a different country, and I've highlighted a few of the countries where it's been held in the past that I've had the privilege of traveling to. It's been a wonderful opportunity to go to different countries and experience the culture and the food and everything, and all the while kind of taking a team of top high school students with me to compete in this programming contest. They actually have these Olympiads in all of the major scientific disciplines. You might have heard of like the International Math Olympiad or the International Physics Olympiad. So the International Olympiad in Informatics is the computer science analog of those contests. And so every year we bring the top 4 students in the United States to the IOI. And I tell you, it is quite a spectator sport. If you're looking for a thrilling sport to watch, competitive programming, to some of us it's exciting, but it's a lot of people writing code in a room for like 5 hours. So as a coach, I'm sitting here watching the scoreboard during the entire event, and kind of you can see our students going up and down in the rankings and everything. But it's not exactly football, but it is very interesting. Some people actually kind of talk about competitive programming as a sport of the mind, I guess. So it's actually quite a vibrant community, the competitive programming community. Lots and lots of programming competitions out there, lots of resources online for those interested in getting into competitive programming. So the IOI, this contest that we attend every year, it really is the premier contest at the high school level in computer science, in programming. So if you go to the IOI, that is a wonderful asset for your resume. Colleges notice that. If some of you were saying before the talk that you want to go to MIT, MIT will definitely notice if you attend the International Olympiad in Informatics, or if you place very highly in one of these other Olympiads, because these are very competitive at the highest levels. And the students that do well in these events are remarkably proficient in programming. They have trained for many, many years in several cases. But you also don't have to train for 10 years to get good enough to participate in these contests. We also have a lot of students that start out and within like a 1-year time frame have actually improved quite a bit. I'll tell you a little bit about our process of training and selecting students through the USA Computing Olympiad. So this is kind of a subset of the world of competitive programming, where generally a contest involves trying to write programs that solve kind of algorithmic tasks. So you have to write a program and you're judged on how fast your program runs. If it runs in like less than a second, then you might get full credit for that problem. And it's a fascinating thing to compete in because, well, I mean, for one, it's a wonderful way to improve your programming skills, to take part in programming contests, because you get to not only learn about interesting problem solving strategies and whatnot, but you also get practice writing programs in a time constrained environment. which can be wonderful, like in a job interview setting. If your interviewer says, hey, how would you solve this problem? Most people who have taken competitive programming classes or contests do a very, have a much easier time with job interviews because they're used to coding in a time-constrained environment. If you do well in competitive programming and have lines on your resume documenting that, that can help you with getting into college or getting scholarships or job offers. All sorts of good things can happen. And some programming contests even have cash prizes associated with them. But I think it's mostly just fun. It's a fun activity that I always enjoy participating in. So I had an early start in competitive programming. I was actually on the U.S. team back as a high schooler that competed in the IOI in 1994. Someone was asking how old I was, so you can kind of do the math on that. And then I've also competed in quite a few other programming contests over the years since then. There's another big programming contest called the ACM contest that happens at the college level that I've also competed in. And then since then, I've been involved with the USA Computing Olympiad. That's the USA organization that selects and trains people for the IOI. And I've been involved with that for probably two or more decades now. I've been the director of the organization for the last decade. So what is the USA Computing Olympiad, the USACO? It's an organization that we provide online training materials and online programming contests to basically promote algorithmic problem solving at the high school level. And so we have a variety of online contests that we offer throughout the academic year. And the result of the contest is we end up choosing the top roughly 24 students in the country and inviting them to a summer training camp at my university for about a week and a half, where we teach advanced concepts and we have a lot of fun along the way. And then from there, we choose the top 4 to represent the USA at the International Olympiad in Informatics. Even making it to our training camp is a huge honor. That is an accolade that will probably earn you admission at many top universities. So lots of fun stuff. We study, very serious, difficult problem-solving techniques, but we also try and have a lot of fun along the way. So here's some pictures of students at our training camp having fun with various activities and programming contests and games that we're all trying to kind of compete in. So it's a wonderful experience, and hopefully I'll have a chance to see some of you guys in the future at our training camp. So how do you get there? USACO competitions are completely free. Anyone can participate, even non-high schoolers. So if you're a college student or an adult, you can also take part in our contests, but we rank them. We rank high schoolers separately from non-high school students. So we have pre-college students in one category and then observers in another category ranked separately. And then our competitions are actually at 4 different levels of, well, this is actually an old slide. Instead of bronze, silver, gold, and pre-bronze, we actually have 4 levels of difficulty now. We have bronze, silver, gold, and platinum, platinum being the most challenging. And everybody, when they start in the bronze level, which assumes that you have basic programming knowledge, but not necessarily any formal training in algorithms or problem solving. The bronze level problems are things that we expect you to be able to kind of figure out on your own, just knowing how to program. They're kind of, logic puzzles and things like that. So they're supposedly relatively within reach of beginner programmers. And then once you score well in a bronze contest, you get promoted to the silver division, where the problems get a little bit harder. And then once you do well in silver, you get promoted to the gold division, where the problems get harder still and involve more challenging concepts. So this gives you an opportunity to kind of gradually improve your skills and keep practicing and learning. We also have a lot of online training materials that you can look at that teach the different algorithmic techniques that are common in our problem sets. We also have about 10 years worth of old problems on our website with solutions that you can submit your own code and see if it passes the test cases. So lots of resources available to help you learn and study and improve your skills. Each of our contests is usually about 3 or 4 or 5 hours in length, but we have it set up so that the contest is usually open for about a 4-day window, like usually a Friday to a Monday. And you can choose to take the contest anytime during that larger window. So when you click a button on our website to start the contest, you have a personal timer that starts at that point, and then you can see the problems, and you have about, say, 4 hours to actually write code and submit answers to the problems from that point. And then at the end of the contest, we reveal the overall results and rankings of everybody. So that's the general structure of our contests. But free and open to all, it's an individual contest, so everyone takes the contest individually, although we definitely encourage you to work with, in terms of your training, start a club at your school and work with your friends to learn this material well. But when the contest rolls around, it's at the end of the day, it's an individual contest. But it's all online. You can just take the contest at our website. So it should be very easy and flexible for those wanting to compete. The USACO has been around for a long time, and we can actually point at quite a few of our superstars from the past who have gone on to make a huge impact in different walks of life in computer science. We have a lot of alums of the program who are now famous professors at different universities. So Stanford, Georgia Tech, UT Austin, just a couple of them. These are alums of ours that have really done amazing things in terms of publishing groundbreaking research since their days of USACO. So we're very proud that participants in our, former participants in our program have had a huge impact on the field of computing. We've also had a lot of our alums do very well in industry, with startup companies or very, high prominence tech companies that they've been part of. Just as an example, so Adam D'Angelo, one of our past IOI team members, was the former CTO of Facebook, and he's the founder of a website called Quora. So very well-known person out in the high-tech startup space. So we have a lot of people who've come through our program who have now done very remarkable things and had a huge impact in the field. Let me, just for fun, I assume some of you have taken our contests, but some of you may not have. So let me kind of, for fun, show you 2 example problems that have been old problems on USACO contests, just to kind of give you a flavor of what these sorts of problems might look like. Oh, that's good. So some of you have done a few problems. Oh, how do they score the contest? So the contest is basically scored on how many test cases your program gets right. And there's a time limit. So your program has to have the right algorithm. It has to be fast enough. And the more test cases you get right, the higher your score is. How do you get into USACO camp? You have to be among the top platinum level competitors in the country. So platinum is the top division. So the highest scoring individuals in platinum are the ones that we invite to our camp. There's a ways to go, starting from bronze all the way to silver, gold, platinum, and then the top level of platinum. But like anything, practice makes perfect. There's no magic bullet with this or any other field that you want to get good at. You have to actually put in time and practice, but it's fun. You get to learn a lot of really cool stuff along the way. Which programming languages are the most useful? Most of our higher level competitors code in C++, although a lot of our competitors also use Java and Python. Those are the other 2 languages that are fairly common, especially at the lower levels. So all of those can be effective. Towards the highest levels, usually most people end up switching to C++ though. Okay, how many people are normally in the competition? The numbers have actually grown quite a bit. I think last year we had our first contest with 10,000 total participants overall, all the divisions, which was a wonderful milestone. It depends. There's a lot more students in the bronze division and a lot fewer students when you hit the platinum division. I think there's only slightly more than 200 students in the United States currently in the platinum division, just to kind of give you a ballpark sense. JavaScript is not supported on our contest. Some other contests might support JavaScript. We do support Python. And there are lots of resources out there for those that want to learn more about competitive programming or algorithmic programming. You can find lots of blogs, lots of textbooks even. You can find online training sites. We have on the USACO website a page of resource links that you can look at that gives you, books or online lectures or other pointers to things you can learn from. Let me talk about these two example problems. Actually, in the interest of time, maybe I'll skip the cow photography problem and I'll just talk about one example problem because it's a little bit more visual. So suppose you'd like to hang a picture of a cow on the wall, but we'd like to hang the picture in a somewhat bizarre way. So instead of hanging the picture on the left, like you would normally hang a picture suspended from two nails, you could hang the picture as shown on the right here, also suspended by two nails. And on the right, this is an interesting way of hanging the picture because it turns out the picture is indeed going to be suspended from those two nails, but you can check if you remove any one of the two nails, the picture will fall to the ground. So the picture is kind of collectively suspended by both nails, but if you take one nail out, the picture will fall. And that's not true on the left. On the left, if you take one nail out, then the picture will fall a short distance, but it'll catch on the remaining nail. So it still will be suspended. And so the question is, can you write a computer program that automatically figures out this really crazy winding pattern of the rope that holds the picture up so that it is suspended by both nails? But if you get rid of one nail or the other nail, the picture would fall to the ground. And it turns out that this problem, even though it looks really quite mind-boggling the first time you see it, has a relatively easy solution to it. You can actually describe the winding pattern as a series of clockwise and counterclockwise turns around the nails. So this kind of really crazy looking winding pattern, I could describe it to you as go around nail 1 clockwise, then nail 2 clockwise, then nail 1 counterclockwise, then nail 2 counterclockwise. That's this exact pattern. And you can actually tell that this works because if I remove one of the nails, like if I remove nail 2, then essentially all the nail 2 entries in this sequence don't matter anymore because nail 2 is gone. And what do I have left? I have go clockwise around nail 1 and then go counterclockwise around nail 1. And what happens if you wind yourself clockwise and then counterclockwise over the same nail? That kind of undoes itself. It basically falls right off the nail. And so this particular pattern, you'll notice if you take out nail 1, then you have 2 clockwise next to 2 counterclockwise, which cancels. And if you take out nail 2, then you have 1 clockwise next to 1 counterclockwise, which cancels. So you get cancellation of the entire sequence for any nail that you take out. But if you don't take a nail out, nothing cancels. You don't have a clockwise next to a counterclockwise for the same nail. And so you can actually generalize this, if you want, to even more complicated patterns. So this is an example if you want to hang a picture from 3 nails, so that if you take out any one of the 3 nails, the picture will fall to the ground. And it's based on the exact same principle. You're trying to find a winding pattern of clockwise and counterclockwise turns, so that if you take out any one nail, everything cancels from that point on, because you're winding clockwise and then counterclockwise over the exact same nail. And so you could, of course, then say, well, what if you have 10 nails? And then you get a really crazy looking pattern that has, almost 1,000 different turns in it, which you probably would not want to try and visualize. So this was just one example of, this might be more like a gold level or easy platinum level contest problem, because it is a bit harder. It requires, a good bit of insight into the solution structure to be able to write a program that will generate these large sequences of clockwise and counterclockwise turns. So just wanted to kind of illustrate one problem that has kind of an interesting visual component to it. So I've really benefited a lot in the past from participation in these programming contests. It's made me a better problem solver and a better researcher and a better teacher. I've learned a lot of really interesting techniques that have not only helped me in my own career, but my success as a competitive programmer is probably part of the reason I got admitted to MIT as a student. It's part of the reason I got hired as a professor at Clemson, because it helped me solve problems and get good results in my research. So I think it's been a big benefit to me participating in these sorts of programs. Finally, some people ask, who have competed in the USA Computing Olympiad, what's with all the cows? One of the fun, whimsical things about our problems is that they're all about cows. It just kind of keeps things fun and light. And the history here is that back in 1994, our training camp used to be held at the University of Wisconsin-Parkside, which is a very rural campus in Wisconsin, with not much around but a bunch of cows. And so the coaches at the time for the Olympiad thought, wouldn't it be kind of cute if we made all the problems about cows? And everyone loved it so much that the idea just kind of stuck. And so for 20 something odd years, we have been making problems about cows. And so we show up at the International Olympiad in Informatics wearing like cow themed t-shirts and everything. Every year we have a cow that is kind of on our t-shirts that is dressed up in the national kind of tradition or garb of whatever country the Olympiad is in. So so we definitely try and still have fun with all of our contests. So they're all about Bessie the cow and her arch nemesis, Farmer John. So just to kind of keep things fun. I'll probably skip over this. So USACO has a lot of challenges facing it as an organization. Participation levels could always be higher. One thing that I care about a lot that I think we're moving in the right direction is gender diversity. So right now we have much lower numbers of female participants than I would really like to see. But we're moving in the right direction there. And one exciting development is that we are now competing not only in the International Olympiad in Informatics, but in a new high-profile international contest called the European Girls Olympiad in Informatics. This is the analog of, there's another one also in mathematics that's a European Girls Olympiad in math. And so we're now training the top female students in the country to participate in this contest and bringing them to our training camp. So I'm hoping that this will help kind of provide more gender equity in our participants. So still lots of challenges along the way to work on as director of the program, but I'm enthusiastic about what the future holds for USACO. That's basically everything I have in my talk. And so I'm happy to address any questions you guys have about computing, my own work in computing, the USA Computing Olympiad, whatever you guys want to talk about, I'm happy to talk. Can I go through the cow photography question? Let me maybe wait till the end until we've finished all the other questions, and then I can go back to that for those interested. What do I think about Scratch? Scratch is a very cool language for learning, for kind of initially learning to program, because it eliminates a lot of the headaches of programming because you just kind of drag and drop shapes together. So you don't have compiler errors or all sorts of complicated syntax to learn. So it simplifies a lot of things about programming initially. But then there still is a bit of a jump going from Scratch to a kind of a real programming language, so to speak. What language is the best to code in? Everyone has a different opinion about that. So some people in competitive programming would probably advocate for C++, but if you're doing, say, machine learning, Python is very popular. If you're doing web programming, JavaScript is very popular. It really depends on the application. There are lots of different things you can do in computer science, and sometimes there's a different language that's the right language for the task. How should you study programming? There are lots of resources out there. In fact, the organization that I'm speaking with here, Easy Fun Coding, has a lot of classes I think that you can take that will help teach you introductory programming.
Excuse me, can you show the previous slides about the European goal? I think that.
Yes.
Okay, thank you. And how many kids attend the Platinum contest each year?
How many total in the Platinum contest? There are just over 200 US students, I think, in Platinum at the moment.
Okay, how many in the gold?
Gold, I don't remember off the top of my head. I would guess maybe, if I just had to guess, maybe 500 or 600-ish.
5 or 6, but like 10,000 for bronze.
Once you get to bronze, you're in the low thousands for bronze. So the numbers go up for each lower division.
Thank you.
Average age of acceptance to silver. I'm not sure. We actually don't track the ages so much of our participants. So I'm not sure. There's a wide range. We have some very young students and then some older students as well. How do you go through the process of solving questions when they're long and wordy? That's kind of also an art. A lot of times when we create a problem, we add a lot of irrelevant things to the narrative about Farmer John and all this stuff, when the problem itself is actually quite simple. So part of the art of problem solving is to kind of boil down the problem to its essence and figure out what the important parts of the problem are.
When's the next meeting?
The next meeting of this seminar? I'm not sure about that.
Yeah.
We have another one coming up on December 3rd. Yeah, same time.
Okay.
If you're interested.
Oh,
Can I recommend a book about algorithms?
10月3号 I'm only in 3rd grade, so but I don't understand C++ yet.
So you
That's
can,
okay.
you
Can I
can definitely
join
get
even though
started
I'm in
without knowing
grade?
C++. There are lots of other languages out there that are kind of more beginner friendly, and there are lots of contests out there that you can use languages or even that don't require programming languages as complicated as C++. So you can definitely get started with languages other than C++. Oh, when are we releasing the contest dates? Very soon. So we're still finalizing the schedule for the next season of the USACO. So keep an eye on our website. We should be announcing, and hopefully this weekend, the dates for the next season of contests. They'll be very similar to what they were last year. A good book about algorithms, I would recommend look at our resources page for the USACO website. I've got a couple of good books listed there. Can you have the recorded video? I think this is being recorded, so I think there should be a recorded video that you guys can have access to. Yes, there's a USACO guide that was recently developed by some of our students that's extremely good as a resource. I definitely would recommend looking at that for problem-solving techniques and such. What's the difference between Python and JavaScript? They're just different languages. The USACO guide is not a book, it's a web page. So you can just search for USACO guide and you should be able to find it.
Okay. Brian, I see probably a question from a parent that said, I think learning computer science and programming is really important, especially for children. However, my children have no interest in learning coding. Do you have any suggestions on helping kids get interested in coding?
I think these contests can actually be kind of a fun way to get into programming because it kind of makes programming fun. It's also, I very much agree that learning programming is important. Some people are calling it, the new literacy. It's just as important as reading and writing, learning how to program, because in the future, almost anything you do is probably going to involve writing programs. But yes, I think I would probably recommend looking into programming competitions or computational thinking contests, because they can be a very fun way to kind of get immersed in the world of programming.
Yeah, I think it also depends on the age. Yeah, for young kids, like you said, you can start from scratch. That really can get them excited, get them interested. Also, they're like Roblox or Minecraft. They can also work with programming language. You can use Python or Java to work with Roblox and Minecraft. That's a good way to get them interested.
There's a lot of fun. Yeah, if you look at, I think what code.org has a lot of really great resources for young students that are starting out with coding, and resources that are very engaging that kind of make programming fun. A lot of them have kind of a video game or a graphics or a robotics sort of tie-in. So lots of options for those getting started with programming. Is it better to learn multiple languages? It's probably good to start out with one language and get good at it. And then once you've learned one language and you kind of learned how to program, then learning other languages is less difficult. Do I have any recommendations for turning pseudocode into real code when solving problems? That's mostly just practice. The more familiar you are with a given programming language, the easier it gets to kind of express your thought process in code. But that is a challenge. A lot of my students tell me, I've got the right idea in my head, but how do I write it in code? And that's what practice will help you with. How much practice do you think you need? It's different for everybody. Some people will tell you to solve dozens of contest problems before you reach the very highest ranks. And there's probably some truth to that. If you want to reach very high ranks like in USACO, you do need quite a bit of practice because there's a lot of different techniques to learn along the way. But I think you can actually get quite a ways into into the system without a huge amount of work that you put in. What percentage of the competitors are girls? We also don't track that. We probably should. So kind of in general, I think the numbers in high school computing, it's about 20% female, or at least it has been in the recent past. And I think our numbers in bronze roughly were about that level. And sadly, the numbers seem to shrink though in the higher divisions. So definitely want to encourage as many females to compete in our contest as possible. That's one thing that I'm kind of passionate about is trying to level the playing field in terms of gender in whatever ways we can. What's the name of USACO? It's the USA Computing Olympiad. That's what USACO stands for. What else do I do besides programming? Many things. I play music, I like to cook. Lots of things that mathematical minds kind of enjoy doing. I think, yeah, I've been kind of rambling for a while now. So if you guys are finished, I'm happy to wrap things up for those who are finished.
I see there are a couple of questions asked about going to gold or platinum level. How many hours do you suggest, the students spend on training every day, or no?
It really does vary per person. Some people probably can make it up to, especially if you've done a lot of mathematics in the past, that usually helps with kind of the mindset for solving these sorts of problems. If you've done a little bit of programming in the past, that can definitely help. So it really does vary. It's hard to kind of just say, oh, after 50 hours, you'll be able to move up to gold or something. It's you might be able to get other people's answers to that question if you look online to see kind of what other people suggest on that. But I'm not sure I have a firm number in mind that would work for everybody.
Let me see, we still have some questions. What language would you recommend for a beginner? If you're really young, start from scratch. And I think a good language to start with is Python. What do you think?
Python is a good language to start.
Yeah, I think it's easy to learn, and yeah, it's also very powerful. You can do lots of cool things with it.
I guess I should probably, this is my USACO official PowerPoint podium picture here.
Okay, so do you guys, I heard you divided your finalists into two groups, right?
We typically do. We have, of the finalists we bring to camp, we have the veteran group that kind of has been to camp before, and then we have a more beginner group that has not been to camp before, and they have slightly different curricula at camp.
Okay. And when you choose the, the final team, do you tend to choose from the veteran group or the new?
We tend to choose from the veteran group.
Okay.
Anyone who comes to camp is eligible for the team, but typically it'll be someone from the veteran group because they just have more experience.
Okay. Well, that's a really enlightening and entertaining talk. Thank you. I see we have one set like 160 students.
Wow. Okay,
yeah.
That's impressive attendance. I hope I didn't bore everybody.
Okay, let's see. What mathematical subject is helpful for USACO? Algebra,
that's a
counting?
good question.
Yeah.
So I would say probably kind of counting and combinatorics are useful. Algebra, probably to some extent. Geometry is certainly also useful. Some little basic bits of number theory, perhaps. Group theory might be a bit advanced. We try not to design questions that depend on advanced mathematical knowledge. So what you really need is just kind of a certain level of mathematical maturity and problem-solving skills. But kind of counting and combinatorics, things like permutations and combinations, that type of skills, those can be useful.
Okay, so Sarah asked this question a few times. Is there a most important language? I would say no, right? But if for
Not
USACO,
really. I think every language is useful for certain things. And so I like the recommendation of Python as a beginning language. That's also used a lot in artificial intelligence. So if you're good at Python, you can do a lot of very cool, relevant things in practice.
Yeah. Seems Brown's level question are getting more and more difficult. Is that right? I think it's actually getting easier, right? The old
it's hard to say because like as a coach, kind of my perception of it is probably skewed. I know that we have in the past probably erred on the side of too much difficulty for some bronze problems, and that's on us. So we try and design the bronze problems to be as accessible as possible to new students. But sometimes it's hard to predict in advance how difficult any given problem is going to be. So sometimes they might be a little more difficult than we intend.
When's the next content? It should be in December, right?
Mid-December. We'll try and post the schedule as soon as possible on our website.
Okay. Let me see. How can you control time limit like big O notion? Yeah, I think you need to learn a little bit algorithms, just to read basic tutorials about big O. It's really actually easy to understand.
Good advice, yeah.
Can you give more information about the camps? So you have to, I guess, make sure to platinum level, right? In order to.
Right, so the camps, we typically invite the very top students in the platinum level. We invite about 24 total students. It may be more than that this coming summer because we also are training our top female students for the EGOI as well. But during camp lasts for maybe a week and a half, and we have advanced lectures, we have kind of fun challenges, we have enrichment, we have speakers that come in and give talks at camp. It's a lot packed into 1 week, but everyone I think has a good time because you get to hang out with a very cool group of fellow students that shares the same interest as you. I can definitely go through the cow photography question, but probably should finish up the other questions first. And those who want can probably head out by that time. Oh yeah, USACO does allow different programming languages, but we have a slightly different time limit for some languages. So Java and Python get twice the time limit as C++ because they're slightly slower languages. Yeah,
Java and Python got 4 seconds, right?
That's
C++
right.
got 2 seconds, yeah. And the same amount of memory, right?
Right, yes.
Okay.
You can find most of this information on our website, which admittedly is in need of a bit of an overhaul. It's sometimes hard to find the information. I get a lot of email questions that do appear on the website, but not in an obvious way. So I'm hoping to kind of update the website to make it a little more intelligible in places. Yes, USACO.guide is a much more modern website. USACO.org is illustrating my old-fashioned web design skills, which are not up to modern standards, unfortunately. What is easy fun coding? Uni, you probably can answer that, I guess.
Oh, okay, easy fun coding. That is, a company I started like 3 years ago from my home. So we teach K-12 students coding classes at different level, from beginner to intermediate to advanced. So we teach children Scratch, Minecraft, Python, JavaScript, web programming. We also teach students Java and prepare them for AP computer science exam and artificial intelligence and machine learning, and help them do extracurricular projects. And we recently actually started to provide USACO training because some of the parents actually and students ask for it, and they really hope to participate in this great contests.
That's really good to hear. That's one thing that I've heard a lot of demand for is classes that can teach the curriculum that helps students get into USACO. And there are places like the Bay Area that have had available classes for quite some time, but other regions of the country, not so much. So it's great to hear that you guys are teaching things like this.
Let me see. How do you, okay, I see a question asked a few times. When's a good age to switch from Scratch to Python? It really depends. You know, some kids, they start doing Python at 6 or 7. Yeah, some will have to wait a few years more, but I think maybe at 10, yeah, most kids should be able to do Python.
I would agree with that, yeah.
How is coding being judged? They have test cases, so you just have to pass all the test cases within the time limit.
It's all automatically judged. So as long as you solve the test cases by the time limit, you get full credit.
All right, let me see what other questions we haven't answered. Can third graders join the contest?
Sure.
I think
there's
yes.
no age limit on the lower end, so you can be as young as you want and participate.
Yeah, I think we have a elementary school student who joined the contest.
Wow. Okay.
And got 4 score.
Wow. Okay, that's
Yeah.
very impressive.
Are we doing? Okay, what else?
It looks like the questions in the chat are slowing down. Maybe for those who want to enjoy the rest of their Friday evening, then feel welcome to be excused, and I can go back and talk about that cow photography question for those interested. The problems seem to be a bit vague. They're not intended to be vague. So if there is any sort of ambiguity about a question, you're always welcome to email me in the middle of the contest saying, hey, can you clarify this? But we do try and make them as precise as possible. There is the extra narrative about Farmer John and the rest, but we do believe that the problems are written, you know, in a well-specified way that at least does correctly convey everything that needs to be conveyed. We're human, so sometimes we could edit the problems better, but we definitely are not trying to make the problems vague. So I can talk really quickly about this other example problem. Sample USACO questions, you can look at the USACO guide website, or you can find on the USACO site the past 10 years worth of problems with complete solutions. So lots of examples out there. So for this cow photography problem, you have all the cows lined up in a row, and Farmer John is trying to take a picture of the cows, but right before he can take a picture, some of the cows move. And so you actually get a picture of not the correct lineup of the cows, but a slightly different lineup after some of the cows have changed position. And Farmer John is frustrated, so he lines up the cows the correct way, in the order that he intends to take the picture, and then he tries to take the picture, but again, some of the cows move right before he takes the picture. And this happens 5 times. So what you get as input is not the correct ordering of the cows, but you get 5 different orderings that each of them is the correct ordering after some of the cows have moved. And your goal is to figure out what the correct ordering should have been, given that the one constraint is that each cow only moved in one of the 5 photos and stayed put in the other 4 out of 5. So the cows didn't move all the time. They can only move, each cow can move in at most one of those 5 photos. And so you have to somehow reconstruct what the correct order should have been. And so this is actually one of my favorite problems that I've come up with in the past. So one way to solve it is if you look at a pair of cows, you know, 2 cows, X and Y, in one of the 5 orderings, X might have moved. In one of the 5 orderings, Y might have moved. But in the other 3 orderings, X and Y are in their original positions. And so if you're trying to figure out if X should be before Y or after Y, you can kind of do a majority vote. You can look at the order of X and Y in all 5 orderings. And if X is before Y in at least 3 out of the 5 orderings, that means X is before Y. Because X and Y can each have moved in at most one of the 5 orderings. So that lets you compare any 2 cows. You can kind of take a majority vote between all 5 orderings to figure out if one should have been before the other. And if you can compare two things, you can sort. And so this is basically a sorting question. You have to sort the cows in the correct order using this compare function that looks at the 5 orderings and takes a majority vote. So that's the intended solution. This was an easy platinum problem back when it was asked.
Okay, I saw a parent ask a question a couple of times. He said, my child is kind of, all right, okay, so said my child kind of have a normal IQ. Do you think he can compete in USACO contest?
It's really a function of practice. I don't believe that like some people are just innately better at programming or problem solving. It's really a function of how much effort you put into it, how much practice you get. The more practice you put in, the better you will get. For me, like I spent an insane amount of time programming. I was really, really bad. I'd be very embarrassed to share some of the programs I wrote when I was a youngster. Back then it was actually really hard because there wasn't an internet to look things up on. So we had to kind of learn it the hard way in many cases. But it just takes time. I think anybody can be a very good programmer if they put in the effort.
All right, does anyone have any other questions? Well, if not, okay, I think we are gonna conclude. Well, thank you so much, Brian, for speaking to us today. Yeah, we really appreciate it. I think, yeah, you have done a lot for the community, and we truly appreciate it. USACO has been a great resource and foster a great, community. So we want to thank you for the work, for your time and effort for promoting computer science education among K-12 students and, train a talented computational problem solving students. Great job. Thank you.
Thank you so much.
Okay. Thank you very much. So that's all for today. We thank everyone for joining us today and hope you guys have a great Thanksgiving next week. Thank you. I see you next time.
If anyone has follow-up questions, you're always feel welcome to send me an email. So.
Thank you. Bye-bye.